All right, let's talk about some gas today. So we learned about moles in the solids. So before we move on to the gas laws, okay. It's gonna be a little interesting if you thinking about the real day examples. But there are a few things you need to memorize at the end of the lesson today. So that's something I will tell you too. And let's see. Oh. Okay, let's talk about gas or gases. Do you guys remember, module 1, probably in the chapter 1 or 2, or it would be like your first or second lessons in your high school, okay? The difference between solid, liquid, and the gas. Do you remember them?
The space in between the molecules.
Oh, good, okay. Can you specify? Let's start off from the solid to liquid to gas. So in solid form, what happens in here?
They're like pressed together.
They're close together, so are very dense and close together like this. So as if there is not much, not much like a gap between the molecules. Good example of that is, if you guys remember the lattice structure of the metals or the ionic compounds. Brandon, you okay with that? Yep. They all comes in what? Comes in a solid, in the room temperature. Why the metals comes in a solid? Because they are the lattice structure, means they're closely packed together, or they're in the network system. But thinking about this, so they are packed, good, okay. But what about in terms of the internal energy? Like, let's think about this. If something exists in the forms of solid, I'm giving you the example of the ice, for example. As ice is what? Your solidified form, solid form of the water. So if in terms of the ice, thinking about the temperature of the ice, do you expect to have the ice in the high temp or low temp? Relatively low temp, about below 0 degrees Celsius for the ice. So it means that in terms of the particles, do you think they would have much energy, or do you think the particles are energized? We don't say that. So they are the less kinetic energy. Simply, kinetic energy means the energy like moving around. In other words, less vibration. So some textbook using vibration in terms of the kinetic energy. I use both actually, because vibration means they are like, so in ice form they're like stand still like this. They're calm. They're not moving around. They're lack of energy. This is why they're kind of closely. Okay, they are able to closely pack together. Make sense? Okay. But in liquid, they started to be apart like this, a little apart. So, and then they are kinda moving around freely compared to the solid. For example, liquid water. Okay, and they are less packed, and there are greater kinetic energy. It means that there are more vibration. So anything like, so this is why the liquid water in your water bottles are kind of free to move around like this, unlike the ice. You see that there are more spaces. You can say there are more spaces in between these. So this is very important to remember. So less energy means there are more spaces. Greater energy means there are more spaces in that case. Now, last one. This is something we're going to study today. Gas. Brandon, what can you tell me about the gas then? Physical state of gas.
They have a lot of space.
The lot of space. So if I take a 1, that would be over here. Or maybe in here. Okay. Okay, there's a lot of space. So there's a vapor or steam. So more space. So never packed. So they're freely moving around. Freely moving. What else? What about in terms of kinetic energy?
They have the greatest.
the greatest. Okay, this is the key to understand the gas laws. Means that giving the heat, making the temperature above the boiling point, the melting point, it simply means that we're putting some heat energy into that chemical. Make them molecules to freely move around. Therefore, they'll be reaching to some sort of state called the gases. So H2O it can be written actually as a solid, it can be written as a liquid, and this time we write as a gases in the state. Does it make sense? It all depends on what they may consist of the same molecules, same compositions, but they all depends on what amount of heat energy, amount of energy they have. This is a key to understand the gas laws today. All right. Any questions about heat? So all the definitions I give you here as well on your page 2. We're here. It's given that too. Feel free to write your notes, but okay. All right, let's talk about the kinetic molecular theory on page 3. Okay. All right, the first thought point, gases are composed of small particles, are the atoms and molecules, same molecules. Think about the water again. The volume of particles in gases is negligible compared with the volume they occupy. Consequently, most of the volume occupied of gas in the empty space. So as you can see, there are more spaces available compared to other states in the gases. This is the key. Now, gas particles move rapidly in the random straight line motions. So this is why I'm going to bring up a little bit of the physics here. This, kinetic energy is equals to half mv squared. Have you seen that before? Yeah. Are you dealing with that now?
Yeah.
Are you struggling?
No, it's fine.
That's good then, okay. I'm going to use this bit of like thermodynamics here, which means that, do you guys remember something you learned in year 10? Energy cannot be destroyed. Yes, or?
Created or destroyed, only transferred from one form to another.
It will be either transferred or transformed. Good. Now, thinking about here, if I put on heat, heat is what? Heat is some form of the energy. If I put a heat, if I put the stove on the water, what I'm doing is in chemistry, we're saying that we're transferring heat energy from the fuels to the water. Therefore, each of the individual water molecules are receiving some energy. Then, according to the conservation of energy, the energy is that heat energy is transformed into the kinetic energy, which is the kind of result of moving around rapidly.
Yeah.
Make sense? So I'm using that half equals to mv squared, but you will never ask to use that formula in the chemistry. There's something more in physics. It's good to know because m is same, v means the increase in kinetic energy means what? Yeah, as k is a half mv squared, we have a fixed, this is a constant value, which means the increase the kinetic energy means increase the velocity. This is the way we can think about their kinetic molecular theory in chemistry. Does it make sense? Okay. Yeah. We'll learn more about the thermodynamics in module 4. It's all about the energy, all about the enthalpy or entropy. That's something related to module 3 of the physics too. All right, any questions about the state of the gases up to here? Pretty easy. Okay, so a bit of common sense we use. All right, talking about the volumes. Yeah, there's a reason why I'm bringing this one here again. Volumes are basically the space we are occupied by the molecules in chemistry, right? Then we are using various units in the volumes. Okay, the standard unit in chemistry is a liter. We don't use milliliter for a standard unit. So if you need to find something in the standard unit, make sure you convert that into liter. There are some cases we have different unit of the volumes too. For example, we have 1 mil, 1 liter, 1 meter cube, or sometimes 1 dm cube too. You need to be familiar with the unit conversion. So for example, 1 liter is how many milliliters, Sky? 1 liter is how many milliliter? 1,000 milliliter, or say 10 to the power of 3 milliliter. Okay, what about 1 milliliter in the liter, Brandon? Converting, which is 10 to the minus 3. Got to get used to with the 10 to the power from now on, because you will be asked to fix your answer in the given thick values. Okay. All right, so this is the kind of familiar things we can use too. What about this? 1 meter cube. is equals to? 1 meter cube is equals to 1,000 liter. Why? Why? 1 centimeter cube, it's given here actually, is equals to 1 milliliter. Thinking about the relation between meter and centimeters, okay, cubing out of that, we get the 1,000 centimeter cube is equals to 1 liter. That is what? 1 meter cube as well. Okay, that unit conversion, that units will not be given on your formula sheets, by the way. So it is important. Micro and nano, sometimes when we deal with the grams, the mass will commonly show up. So that's something we're going to deal more. We're going to do more practice when we're dealing with the chapter 3 questions. Okay, that's one example of units of the volumes. All right, let's do some questions on your page 5 now. A gas has a volume of 255 milliliter. What is the volume in cubic centimeters? What is the volume in the liters? What is the volume in the cubic meters? I give you 2 minutes to try these questions, and if you have time, you can try the next one too. Calculator, anyone?
I have one.
Yep, bring your, take it out. You may need to use it. Okay. So question A, we need to convert the 255 milliliter into cubic centimeters. As 1 milliliter is equals to 1 centimeters, this is equals to 255 centimeter cube. Easy. Okay. B, the liters as with the milliliter is the 10 to the minus 3. So this is a way. You can write this as 255 times 10 to the minus 3 liter. That's one method you can do. Okay, and then what you can just play with the dot, so you can go for 2.55 10 to the minus 5, or 10 to the minus 2, minus 1, sorry, 1 liter as a conversion. Or you can simply say that is 0.255 liter 2. Okay? So, but don't leave your answer in the first one here. I want to see your answer either in this or this. Because this is what we need to say that we're scientific, like in a way we're writing the numbers again. Good. C, what is its volume in cubic meters? Okay, so to convert that to cubic meters, as we know, the 1 liter is equals to the 10 to the minus 3. So using that, so that to 0.255 liter is same as that times, or 2.55 times 10 to the power of minus 4 cubic meter like this too. Okay, so cubic meter is not really used a lot in chemistry because we don't really deal with 1,000 liters. That's actually the volume of the swimming pool, 1,000 liter. So all like something very similar to swimming pool. So we don't really deal with that a lot in chemistry, especially in the calculations. But you know, you never know. Okay, some scientific freak do that. Okay, or when we're dealing with some environmental problem, we probably use that volumes too. Good. Next one. A gas has a volume of the 700 milliliter. All right, Brandon, what is the volume in cubic meter for 700 mil? Just thinking about the relation between this 700 milliliter into cubic meter. Cubic centimeter, sorry.
Oh, 700
700. Good. B, what is the volume in the liters? So we have 700 milliliter in the liters. Sky, that is in liters.
7 times 10 to the power of minus 4.
Okay, or 0.7, that is 7.0 times 10 to the power of minus 4, or 7.0 times 10 to the minus 1 liter. Don't leave your answer in the 10 to the minus 4.
Yeah.
I want to see that. Yeah. So it's either these two.
Yeah.
Good. So kind of things straightforward and simple.
Yeah.
Right, now last one. What is the volume of the cubic meters? As we know that 7.0 times 10 to the minus 1 liter is converted into 7.0 times 10 to the power minus 4 meter cubic meter. This is one thing you can remember too.
Yeah.
Good? It is possible because we are dealing with the gas, and you can imagine about gas compared to the liquid. I mean, thinking about this, I would say about 600 mils of water. Okay, Brandon, I want you to imagine about if you vaporize this everything in the water here, vaporizing 600 mils of water. Thinking about the volume, do you expect like the steams actually can spread out all around this room too? Compared to like even that 600 mils, when you're steaming that, vaporizing all the water molecules, the steam can actually fill in up the whole room in here, or maybe the whole building, because that's what the property of the gas. Right, let's talk about the pressure too. So this is other factor we need to concern when we're dealing with the gas. By the way, we don't really deal with pressure in the liquefied or solution forms a lot.
Oh,
Yeah, it's more about when we're talking about the pressure, it will be more dealing with the, it's more about the gases, most likely. Now, what is pressure? Let's think about what is pressure. I mean, let's think about when you get pressured. We literally say, oh, I got pressured. I got pressured. So when do you say you're pressured?
When you're being forced to do something.
When you're forced to do something. So there must be I like that, when there's a force applied on you. Okay, when you get a force that you get pressured to. Sky, what about you? When do you use the word, oh, I feel so pressured?
Same thing.
Same thing when you get forced or when you get stressed.
Yeah.
When you get stressed out, you said, oh, I'm so pressured. Or when you're thinking about just physical meaning, that's more like in the psychological, mental things.
Oh.
But thinking about going to school, Brandon, probably you know that you're going to circular key. So in the rush hour, 8 o'clock or like at 7:30, you know how bad the traffic is. You know how bad the public transport is now, fully packed. I know because I went to Sydney. I hated it. Okay, I'd rather go late in that case because why? You can feel someone's touch. You can feel someone's you can get pressured. Why? The train's capacity volume is limited. We can't really stretch because we have many people. That's impossible, unless we have more carriages. But thinking about one carriage, we can't really stretch the volume. So I call that as we have the same volume all the times. But if we have more number of the people inside of the one carriage, that's when we say you get pressured. Same thing in chemistry here. Assume that we have two same volume of beaker or some container, saying that one has a few molecules like this, and one has more. So I have 1, 2, 3, 4 molecules. I have countless molecules here. So Sky, which is more pressured comparing these two? The right one is more pressured because you can feel it from your heart. You can feel it from your heart. Oh, this must be pressured. They must be like, oh, this must be so condensed. They must be packed. This is when we're talking about the pressure. This is one method we're talking about pressure in chemistry. And that also applies to the force too. Because when we have more particles, more molecules in the same container, they actually can apply the same force, more force from others compared to this one here. A little bit of physics, because pressure is actually defined as a force divided by the volume. Don't worry about it. Don't worry about it. Okay, we're not going to use that. Another situation is, what about this? I have the same molecules here, same amount of molecules, okay, or same amount of molecules, number 4, but in a small container like this. So these two have the same number of the molecules, but one has the bigger volume than another. So which one do you think is more pressure, Brendan? One top or one on the top or bottom? One on the bottom. This is the case, we have said they're more pressured. So in summary, we have two ways to control the pressure. One is the number of the molecules. Two is the size of the volume. So when the volume is increased, so we say pressure can be increased by either increase the number of the particle or molecules, okay, or either decrease the volume. Does it make sense? Okay, and there are specific units we're measuring that too. But according to the this is called the Avogadro's partial pressure rules too. When we're adding up all these here, assume that we're putting in the big container here. Can you guys see that? I'm mixing up all of these beakers into one big container, one big pot, I should say. Okay, but thinking about the pressure from here, say P1 and P2 and P3. When I'm thinking about the total pressure, P total, in this kind of situation here, I'm just saying, hey, the pressure from here, here is added up together because we did not change the number of the particles first of all. We added up all the number of the particles. So I can tell, hey, the pressure has been increased. Why? Why do I say the pressure is increased in here? The total pressure is increased. Why? Because we're adding up all the particle numbers here. The increased number of the particles. But the volume is kind of increased, so it's kind of maintaining all here. Or assume that the volume, the total volume is same as adding these three volumes. Then the pressure would be increased. This is why we can bring up the P total is equals to P1 plus P2 or P3, saying that these are the partial pressure. Does it make sense? Okay, so this is where the rules are coming from too. Sometimes used, sometimes not, so we'll think about it. Now, units of the pressure. Yes, it might be the first time you're hearing about these units. Maybe not the first time. Have you ever heard about the millimeters Hg, millimeters of mercury? Have you heard about this somewhere? Okay, when you're thinking, go to climate changes or thinking about like some forecast, they're actually giving some pressure difference too. Or we're thinking about when you're going on the plane, they're actually giving some pressure difference in the volume unit of this. Now we have different units as the volume. The pressure, bring up a little bit of physics here, pressure is actually can be calculated by amount of force per the volume, or this about the surface area, should say. I'm using the unit of the force, which is Newton, unit of the surface area, which is the meter square. So the unit can be set newtons per cubic meter, per square meter. But this is something that we don't really use a lot in the real day life. Instead, we use this PA, Pascal. So 1 Newton unit, important to remember, is equals to 1 PA. That's more likely the kind of close to the standard unit we use in everyday life too. Have you heard about the Pascal? Not really, Brendan? Not really. Okay. Pascal is the unit of the, you can just remember that, it's a unit of the pressure, which means 1 Pascal is the same as 1 Newton per square meter. Okay. That is also, it can be converted into kilopascal. It's all written here, by the way. Kilopascal is, the kilo of the Pascal. That would be mean what? 10 to the power of 3 PA, Pascal here. Which means that is same as the 10 to the power of 3 Newton per meter squared. This is actually standard unit we use a lot, kilopascals. Okay, that's important. Now, we also use the unit of the 1 atmosphere. Have you heard of the atmosphere? So atmosphere is basically the pressure we are feeling right now. So sometimes we describe it as a sea level, pressure in the sea level. Means that when you go climb up the mountains, you will feel less pressured. Because it's all related to some physics, don't worry about it. Okay, you feel that. So have you ever experienced like your ears go blunt, go on the plane or in the top mountains? Yeah, because the pressure is different. So 1 atmosphere is something that we feel now is same as the 101.3 kilopascal. And a weird number, but that's something you need to remember. It's 101 kilopascal, 1.3 kilopascals. We also have the unit of the 1 bar. 1 bar is same as the 100 kilopascal. So you should know the difference between 1 bar and 1 atmosphere. 1 bar means 100. 1 atmosphere means 101.3. Now, last one is millimeters of the mercury, or mmHg. Hg is the chemical symbol of the mercury, so we call it mmHg. Sometimes we use that. Is 760. So 760 millimeter Hg, mercury, is equals to 1 atmosphere. That is same as that much of the 1.103 times 10 to the power 5 newtons per meter square, or the Pascal in that case. Kind of tricky, because you never know what units you will get. So started from the Pascal, okay, and the kilopascal, that's not too bad, okay. Probably the atmosphere is one point you get really confused. But this is the most important part of the kilopascal. We use that as standard unit, but sometimes you're given a unit of pressure unit in the atmosphere. Yes?
Why do you need different units?
How do we measure difference, the pressure?
No, I mean, why do you need so many?
Because sometimes we use the mmHg when you have the specific tool using that unit. Like I'm thinking about the miles and kilometers. So, like, it depends on the country. Some countries prefer using the kilopascals. Some country, like some other country, European country, probably using this still. That's been used for like many years, 100 years, and that's kind of new units they introduced, and that's kind of standard unit we're making, and we all agree with. But some, old-fashioned, they prefer the kilopascal sometimes, or sometimes prefer that too. Same for the Kelvin and degrees Celsius in the temperature. Have you heard about like Kelvin? Yeah, or degrees Celsius. There are two different measurements too. So Kelvin was like what we call the standard unit, something we use a lot in the laboratory. But thinking about the Kelvin, the limitation Kelvin is too big. So people get freaked out, say, hey, this is now nice weather of the 293 Kelvin. Rather than we saying like 25 degrees Celsius, we feel more like friendly. It's more easy to use because we hate to use the bigger number. Same in here. Instead of we saying 101.3 kilopascal all the times, just make it to 1 atmosphere. How simple is this? It's more friendly and get close and clear. All right, let's do this exercise together now. So Mount Everest is the highest mountain on Earth. So A, the atmospheric pressure at the top of the mountain Everest is 0.33337 bar. What is pressure in the kilopascal? So, thinking about the relation between the bar and the kilopascal, 1 bar is 100 kilopascal. So we have 0.337 bar is actually same as what? That times the 100 of the kilopascal, which means this would be? Yes, thank you very much. 33.7 kilopascal. By the way, the Pascal unit is actually originated from the mathematician called Pascal too. They're also known as physicians too. B. Atmospheric pressure at the top of Mountain Everest, Everest is 253 millimeter mercury. What is the pressure in the atmosphere? As 760 millimeter Hg is equal to 1 atmosphere. So 253 millimeter Hg is equals to 253 divided by 760. Then what do you guys get? 0.33. Can you give me the three specific values? Yeah. Oh, okay. Yep, 333. 3 unit of atmosphere. So this is the thing, Brandon. When you're giving in the unit of the the significant value of three significant values, your answer must be followed that significant values too. Different to the math. Math, I know we understand that the correction is like 2 decimal points, but here, as we're dealing with lots of the decimal points too, so preferably it's either 2 or 3 significant, but sometimes they can ask you the 4 significant too. So be aware of that. C. The atmospheric pressure of the top of Mountain Everest is 0.333 atmosphere. Oh, it's given here. What is the pressure in the kilopascal? So 0.333 atmosphere, as 1 atmosphere is equals to 101.3 kilopascal. So how do you find that? Kilopascal is then, Sky, how do you convert that atmosphere to the kilopascal? Yeah, okay, so 0.333, then basically 101.3 divided by that. And so what atmosphere is that? So that's basically, yep, 101.3 times 0.333. Isn't it? So that means that 1 kilopascal, 1 kPa is equals to, moving that, 101, 1 over 101, yep, so 101, if that's this, then basically 101.3 times that 0.333, then you'd get 33.7 in 360 in the kilopascal. The atmospheric pressure of the top of Mount Everest is 253 millimeter mercury. What is the pressure in bars? So in 1 bar is 100 kilopascal. So how to convert this? As we have 253 mmHg, and 1 millimeter Hg is equals to 1 atmosphere, that is equals to 101.3 kilopascal. Kind of getting confused? That's okay? So what we need to do, converting that mercury into the bar given. Oh, sorry, the bar. Sure, okay. As we're given the kilopascal of that value, which is 33.7 kilopascal, convert that into the bar is that's simply 0.337. No, divided by 100, yeah. As 1 bar is equals to 100 kilopascal. One atmosphere is equals to 101.7 kPa, and one bar is equals to 100 kPa, using the relationship here. So we're using this, converting to that. A little confused? You okay? Okay. It's more about math, not a chemistry yet. You alright, Sky?
Yeah.
Good. All right, page 8. 9, sorry. There are some questions you can try to now. Can you guys try to do question 4 and question 6, please? 5 is easy. So 4 and 6 now, please. Just checking that I'm having the same page. Oh, we have a little different. Hang on, sorry. Yep, I was using the old edition one. On your page 115, sorry, that's 4.1, isn't it? Yeah. Yeah, this is why you need to use and update it.
Oh.
Yeah, there are 3 questions you can do. Don't forget about the try yourself yet, okay? Can you try to do the 4.1 question, converting the units one, question 1, 2, 3, please? Oh, by the way, the unit with temperature is not really given. That's a shame. Okay. Just letting you know that 0 degrees Celsius is equals to 273.15. Kelvin. That's something you can use to convert the temperature. And 1 milliliter is equals to 1 cubic meter. 1 liter is equals to 1,000 10 to the power of the milliliter, and that's 10 to the power of minus 3 cubic meter. Think about the unit of the bar. One kPa is equals to 1 atmosphere. 1 bar. Oh, what am I? 100. My. Atmosphere is 1 kPa. 100 kPa. 1 bar. Need some drink. Hello, hello. Oh, knew it. Yeah, so there are some more questions on that paper compared to the what you had before. Yeah, I know some of the units are like very it's not really familiar, like especially bar or atmosphere. Sometimes we use in everyday life, but bar or kilopascal is something that we don't really use. But in science, in chemistry, yes, we use them as a standard unit, especially the temperature. Yeah, so rather we measuring something in the degrees Celsius, we use the Kelvin as excuse me. 0 Kelvin is also known as the absolute zero. So that's something we chemically, scientifically, we think that that's the lowest temperature we can get, which is minus 273 degrees Celsius. It's quite interesting. Because in that absolute zero, the molecules are not really vibrating. So they are actually like a frozen. They're not moving around. They just stand still. This is why we call it zero, absolute zero too. Okay, let's do that from the question 1. Convert the following 25 degrees Celsius to the Kelvin. So to convert that degrees Celsius to Kelvin, as the 0 is equal to 273.15 Kelvin, 25 degrees Celsius is 25 plus 273.15. So you should have 298.15 Kelvin. B, 0 degree to Kelvin, the 0 degree is simply 273.15 Kelvin, easy. Last one, 373.15 Kelvin to degrees Celsius. Yep. Kelvin is equals to 373.15 minus 273.15. That's 100 degrees Celsius, like this. Easy. All right, question 2. 2 liters of 2 liters of hydrogen gas are reacted with 1 liters of the oxygen gas to produce 2 liters of the water vapor gas at STP. Now, write it down. STP means the standard, the temperature, and the pressure. Okay, in that standard standard temperature is, we call that the room temperature, which is 25 degrees Celsius, or saying 298.15 Kelvin, and the atmospheric pressure of the 1. So that's what we call a standard temperature first. Okay, or 100 kilopascals should be the standard temperature. Now, A, what is the mole ratio of the reactants and products? So how do you find the mole ratio? We have, in your reaction of the producing water, we have 2 hydrogen gas required for 1 mole of the 1 oxygen molecules to produce 2 molecules of the water molecules. So the mole ratio is simply, it would be 2 to 1 to 2. So H22O to H2O is equals to 2 to 1 to 2. Which means that per 1 mole of the oxygen, there are 2 moles of the hydrogen required to produce 2 moles of the gas, water vapor. B, what is the ratio for the volume of gases? So let's write it down. Volume of the H22, volume of the O22, volume of the H2O. First of all, it is given that the 2 liters of hydrogen, so it'll be 2. And then we have what? 1 liter of the oxygen, 1. And then lastly, we have 2 liters of water, there'll be 2. It's given as that. C, if 10 liters of the hydrogen gas was to react fully, how much oxygen gas would be used and how much of the water vapor would be produced? Okay, how do you do this? So you have to think about here, okay? As we have 10 liters of the hydrogen gas and thinking about the volume ratio here. So if when the volume of the H2 is 10 liters, following to the volume ratio we had in this standard lab means that then when VH2 is 10 liters, then VO2 must be half of this, which is 5 liters, and VH2O must be 10 liters as well. So how much in the question means that how much volume they can produce in here. And we can use the same thing here. So I can change the questions like, if we have 10 moles of the hydrogen gas, Brandon, if I have a 10 moles of hydrogen gas, how many moles do we need to fully react with the hydrogen gas?
5 moles.
5 moles. And how many of the water molecules will be produced? 10. That's how we use the coefficient value in the chemical reactions. And this is why you have to get 100% for your balancing equations from now. If you're not feel confident with the balancing equations, try to do more practice on it, because it will come out like this. Everyone good? All right, let's do the question 3. Convert the following units of the some pressures we have, okay? So first of all, we have what? Unit of the atmosphere. So let's do this. 29 atmosphere. As 1 atmosphere is equals to what? 1 atmosphere equals to 101.3 kilopascal. Okay, and then what we need to do is we need to find in the pascal. So let's convert that into the kilopascal first. So how do we do this? 29 times 101.3 kPa. Yep, and then by doing so, you would get the 2,900, about 338. Did you guys get that value? Was something similar? Maybe.
Oh, 293.77.
Yep, 937, 7.7. Let's take the value too. 7.7 kPa. Now, how would I convert that into Pascal? As kPa is equals to 1,000. Very good. That means times that 2,000. And your calculator will give you 2.9377. Now, as we have 2 cyclic values given here, fix that into 2 cyclic value. That is 2.9 times 10 to the power of 6 Pascal into cyclic value. Okay, Brendan, do you get the point of the converting the into given cyclic value? So we have different cyclic value in question B, which means we have to follow that as well. B, 1.32 times 10 to the power of 2 Pascal into bars. Okay, 1.32 times 10 to the power of 2 Pa into bars, as 1 bar is equals to 100 kilopascal. Okay, first of all, let's think about this in the convert that into the kilopascal. So that is equals to 1.32 times 10, so times that 2. Divided that by 10 to the power of 3, so it'll be 0.132 kilopascal. Okay, and now convert that into the bar by divided by 100. And then you will get the bar, and what was the value, Sky?
1.32 times 10 to the power minus 3.
Very good. And that is in your 3 cyclic value given in your questions as well. Good. Question C, 5 atmosphere ATM into bars. Brandon, how are we going to convert the 5 atmosphere into bar?
First with the kilopascals.
Yep, so atmosphere, into kilopascal. So how to do it? 5 times?
5 times 101.3.
Very good. And you to get? Did you get 5 or 6? 0.5 kPa. Okay, and then
times by 100.
times by 100 times or divide? Divide. So that by 100 would be the bar. So what is this? 506 divided by that is giving you, approximately giving you 5.1 bar in that case, as it's a 2 sig fig. All right, if you're given in the 1 sig fig value only, try to get it into 2 sig figs, because there could be an error in the 1 sig fig value again. All right, last one, D. We have 74,000 bar into the atmosphere. We don't have the 74,000 bar. Sky, how do you convert this into the atmosphere ATM? Shall we convert that into kilopascal first?
Yeah.
Bar into, how do you convert the bar into kilopascal?
You divide it by 100.
Divide or times? 1 bar is equals to?
You divide it.
1 bar is equals to 100 kilopascal.
Yeah.
Means that this much of bar is equals to times 100. As 1 bar is equals to 100 kilopascal. I know, it's getting confused. So that will give you I don't know, 7.4 times 1, 2, 3, 4, 5, 6, 10 to the power of 6 kPa. Yep, and then convert that into what? Atmosphere to by divided by 101.3. Then you'd get, did you guys get the 7,000, 73,000 and 50? Yep. So approximately in how many sig figs do we have in there? We have 2 sig figs. So fixed and 2 sig figs. This is approximately 7.3 times 10 to the power 1, 2, 3, 4. Atmosphere in 2 sig fig values. All right, any questions about the unit conversion? Okay, I mean, it takes a little time, especially about the pressure. I know we didn't really do much practice with the pressure in the real day life. So, and it will take a little time to get adapted to these units, but it's important. So before we move on to gas laws, we learned about the 3 important factors of the gases. One is volume. And the second is the pressure. And the last one is the temperature. Okay, and after the break, we're going to learn about how these factors are all combined, all interacting each other for the gases. All right, let's take a little break. Can't play any piano. Okay, sorry. Hey, let's start some gas laws. So today I will ask you to memorize. Yes, I will ask you to memorize 4 different rules, 4 different gas laws. Okay, and you are required to remember the scientist's name.
Oh.
I know, this is the worst part. You need to memorize the scientist's name. And the name is not that interesting, to be honest. But name can be like kind of familiar if you're interested in some science history. They are like kind of famous scientists in the science history. All right, before we move on to the rules, the laws, gotta introduce something that you need to use a lot. We are going to use lots of this mathematical terms in describing some relationship between some A and B. There's one. When we say the directly proportional, have you guys heard about directly proportional? Yep, it simply means that A and B is when we say A and B is a directly proportional, means that they also have some sort of the linear relationship. Means it will be like that on your page 120. You to see that on your axis of the A and B, they will be like this. Or in other words, you can think about the y is equals to mx, something like that. Don't worry about the b, the coefficient here. We're not interested in here. Some maybe in physics, not in the chemistry. Yeah, that's for physics, not in chemistry here. So simply when we say, hey, A and B is directly proportional, we can say that they have some relations by the K value, which is the constant value. And the K is also be what? The gradient of this linear relationship. So for example, thinking about this, A is equals to 2B, or A is equals to 4B. The simplest way to think about that is, by increasing B by 1, A will be increased by 2. By increasing B by 1, this case, the BA will increase by 4. Therefore, we can expect the gradient value in your graph, A equals 2B, assume A equals 2B, something like this, close to the y-axis. It will be more to that, close to that. So you can bring it up a little bit of the mathematical contents you learned from year 9, 10. Don't need the year 11 contents here. We're not going to learn about sine and cosine in chemistry. You do in physics. Yeah. Oh, yeah. Oh, everything that, you learn about tangent, cosine, sine. It's all about that. Vector is all about that. So, but not in chemistry. We're not interested in any of the trigonometry. But something that you need to remember is, hey, A is directly proportional to B means that they also have the relation of A equals to KB. Simple as that. All right, next one is when we say inversely proportional or the indirectly proportional. Have you guys heard about indirectly or inversely proportional? Okay, have you heard about that, Brendan? Inverse proportional. It simply means that A is proportional to 1 over B. In other words, you can think about this hyperbola relationship. Do you see that, when B is increased, the way we interpret the graph is when the B is increased, you see that B is increased or the B is increased, A is kind of decreased. This is why we say they are indirectly or inversely proportional. So just like what we have done in the direct proportional, we can say the A is proportional to K times 1 over B. That's some sort of the hyperbola relationship. Okay, so you gotta use a lot of words like whether they are directly proportional or inversely proportional to describe these laws we're gonna learn today. Any questions about these two terms yet? Everyone good? Yeah. All right, easy. All right, move on to the first law. It's a law by the Boyle, and known as the Boyle's law. The gas law number 1 is the Boyle's. Boyle's law, and this law is known as the relation of the gas. So everything you're learning today is all about the gas here. So it is about the volume and pressure. Volume and pressure. Okay. Sky, what would be the relation between volume and pressure? Thinking about volume and pressure, this is something I explained today. Indirectly proportional. Why? When the volume is increased, what did I say about the pressure? Okay, how do you explain that? Let's try to think about how you're going to explain that relationship. What happened to okay, assume that we have a certain amount of the particles in gaseous state. When we increase the volume, okay, thinking about the definition of pressure. When we increase the volume, there's more spaces available for those molecules, even though they're excited, even though they have a high kinetic energy. If I provide them more space to move around, Brandon, do you think there will be more pressure or less pressure? Less pressure. Thinking about, rush hour train. Okay, thinking, you have a really luxury train that's really expanded size, really huge size. It means that you get, even though you have the same number of people in there, you get less pressured. That's the relation between these two. Pressure and the volume is inversely proportional like this. In other words, P is inversely proportional to V. Okay? Makes sense? Okay, that's how we say. Or I can say, as we can have here, the combination of P and V is the same as the constant value. In thinking about the relationship here. Because as I said, when A is inversely proportional to B, we were saying A is then K on B like this. Do you remember that? Okay? Means K must be A and B. Now, don't worry too much about the K. K simply means it can be any constant value. And it is important that we have to keep the constant value, because when we say the constant here, it simply means that when we increase the P, V must be decreased to make that compensate the change. Does it make sense up to here? Okay. So Boyle's law is number one is saying P is inversely proportional to V, or PV equals to K. That's the rule number one. Easy. It'll be hard to remember the scientist's name, to be honest. And matching that to the relationship here. So Boyle, pressure, and volume. So I can write that. Pressure and volume. That is, P is inversely proportional to V, or P is equals to PV equals to K. Okay, next one is rule number two. Rule number two is called the Charles. Sounds familiar, Charles, okay? So Charles. Charles's law. And this person is describing about the relation between volume and temperature. That's interesting, volume and temperature. So what would be the relation between volume and temperature? Sky, what would be the relation of the gas and volume and temperature?
Directly proportional.
Why?
Because as we increase the volume, the atoms will be more free.
Yep.
And
So to show the relation, I'm doing something over here. Can you see that in the demonstration here? Okay. Let's move that over there. Okay. So what I'm doing is I put some water in my conical flask. I put the balloons up there. Okay. So in the balloon, I try to evacuate all the gas in here. So let's make some hypothesis here. Scott, what would be your hypothesis of this demonstration? I put the liquefier on now, so.
as the volume will increase because the volume of a liquid, that gas state will be larger than the volume of the liquid state.
Yep. Yep. So in a step by step, when I light the fire, when I'm boiling this, tries to give it boiling this water, let's think about it in terms here. I'm putting some heat energy from the fuel to the water. And the water particles, water molecules are now receiving the heat energy. According to the conservation of the energy, the heat energy will be converted into the kinetic energy. As the particles gaining more kinetic energy, the gap, the space between one molecule and another molecule will be stretched or enlarged. As a result of that, we are expecting that, as you can see the steaming coming out, the balloon will be kind of expanded. As we're putting some more heat energy into that flask here, there are more kinetic energy on the particles. Does it make sense? Okay? More kinetic energy means more space is available. More space means that there are more volumes. Therefore, the temperature and the volume are directly proportional. This is the rule of the Charles's law. I know it's a kind of common sense, I know, but scientists love to put it into the formulas, put it in the relationship, and make it into quantitative values to get the relationship. So you can say Charles's law is about the temperature and the volume, saying that the T is directly proportional to the the volume. Therefore, we can say T on V is the K. some constant value. You can think that as T of V is something like what? Something about the gradient values too. So for example, we have a relation here in the given sample here. We have temperature that's from 20 to 140. As you can see, the volumes are increased from 60 to 84.6. So we are now saying, hey, these two are directly proportional. But if I ask you about, hey, what's the relationship by like going quantitatively, you can find that gradient value of the line. And how do I find the gradient value, Brendan? Rise over run, which means that y-axis on the x-axis. So this is what I mean by y-axis on the x-axis again. That shows the k, which is the gradient value of this graph. Pretty easy. I'm just waiting for this to show that balloons are expanded. It takes a little while. Let's leave that for a while.
Will it expand slowly or really fast?
In that case, it depends on what fuels you're using. Okay, I'm using the ethanol, which is like it's an alcohol burner, so it takes a little more time. As the heat efficiency is not that great. So when you're using some like butane gas, it will be faster. So in Bunsen burner you have in the lab, they'll be much faster to see the reactions. But in that case, to perform the experiment with that, you need to measure the temperature to see the volume increase too. Okay. All right, that's the Charles' law. Again, the name can be challenging. The V on T equals K. Next one is called the Gay-Lussac's law, and he's talking about pressure and temperature. That's double S, Lussac's law. And he's the one talking about the pressure and the temperature. Well, we have a given data here, but let's think about what would be the relation between temperature and pressure. I can give you an example of this again. When it's a hot summer day in a rush hour train, do you get more pressure or not? You get more pressure because what you're trying to do, think about it, like, you're really, you feel really, really hot, not just you. The people surrounding you in the rush hour train. So, you're sweating, you smell. It's kind of nature things. I smell too. It means that what you try to do is when you get really heated, when you get really, when you feel really hot, you try to get more avoid from the others. So in other words, there will be what? There will be more spaces available. This is something we learned in here again, temperature and volume. Now, increasing in volume in the given surface here, try to increase the volume means there will be more pressure. So thinking about like in a rush hour train, I can start to explode now. I start to expand now. Thinking about the train, the hot summer train in the hot summer day, rush hour train, hot summer day, you would feel more pressure. Therefore, increase the temperature means to increase the pressure as well. Make sense? Okay? Kind of make a logical sense here. So I can say the pressure is, temperature is, the pressure, should say, is directly proportional to the temperature. So the temperature P is proportional to that, which means that P on T will also be the K value as 2. Okay. Let me just change that to the relations of the V on T is equals to K, because we're going to combine them all. Any questions about the three laws? We have learned about Boyle's, Charles, Gay-Lussac. So I gave you that in the alphabetical order. BCG. We actually have A, Avogadro's law, but I put Avogadro because it's the most important things yet. So I put BCG first. Okay, how do we remember that? B is for pressure and volume, Charles for C for T and V, Gay-Lussac for temperature and pressure. I know it will be challenging. So pattern is BCG, and it's always be direct, proportional, indirect, direct. Okay, and one is about pressure, temperature, and temperature. So you can find your own way to memorize that too. And it is important to memorize that different laws by the different scientists. And it's going to be challenging, as I said. All right, any questions about these three people? pretty easy. Okay, let's do this question together, 4.2 on your page 126. Yeah, just not enough to boil the water. Stop that. Ooh. What the? Okay, question 1. A helium balloon at 1 atmosphere pressure has a volume of 5 liter. The external pressure of the balloon is decreased to 0.3 atmosphere. If the temperature remains constant, what will be the new volume of the balloon? So let's think about these questions together. What relationship, what laws do you think we need to use? What is the relationship about? Pressure and volume. Is it pressure and volume? Hang on. Sorry. Yeah, it is. Okay. Here we go. So we have what? Helium balloon at the pressure and the volume here. So we have temperature remain constant. External pressure is balloon is now decreased to 0.3. So now you see that 1.0 atmosphere is decreasing to 0.3 atmosphere. Okay, so what would be the volume? What would be the volume of the balloon in that case? So bring it up what? The relation between pressure and the volume. Sky, what is the relation between pressure and volume? Indirect. So when we increase the pressure, the volume will be decreased. So in that case, we decrease the pressure, therefore volume will be, yes. So we can we also think about, hey, pressure and volume, PV is equals to K. Is always be the constant value of product of the pressure and volume. So using that, let's find the constant value first. What we have here is we have 1 atmosphere. Don't worry about the units because we are finding what the ratio value here is. So that pressure is given as 1 times that volume is given as a 5 is equals to K. That is what? 5 is your constant value. Okay, and the K is also same as PV, given that we have a new pressure of 0.3. So that's 5 times the volume again. Then V will be what? 5 divided by 0.3, which is into sig figs. 0.17. 5 divided by 0.3. No, it'll be 16. Or into sig figs, it'll be 17. Unit is what's the unit of the volume? Liter. So make sure in the 2 sig fig like that. Okay. So simply talking about the what relationship or the ratio values in that case. So what, according to what scientists, what law is this? It's about the pressure and the volume, which is the Boyle's law. Okay, then question 2. The swim bladder of the fish has a volume of the 30 milliliter near the surface of the water. Okay, well the pressure is acting on its 1 bar. Assuming no changes to the gas composition of the bladder and no change in the temperature of the water, what will be the volume of the bladder at the depth of 10 meter where the pressure of the swim bladder is 2 bar? So the pressure is now being increased. What is the relationship, what is the 2 factors? What are the things we are looking for here? We are looking for what? Volume and the pressure. Again, volume and pressure are inversely proportional. So Sky, can we say the pressure, the product of the pressure and the volume is the K again?
Yeah.
In that case, so how do you find that? P is equals to what?
30 times 1.
Pressure is given as 1 bar.
Yeah.
Okay, so 1 bar
1 times 30.
and the 30 milliliter. Then you get the constant value of 30 bar times milliliter.
Yeah.
That's your constant value. Don't worry about the units, and just write it for the in that. So I'm giving that exact units. And as the PV equals to K, that is constant value. Then 30 is equals to the new pressure, which is 2 bar. So the P times 2 bar. Sorry, the V should be. Therefore, V, the new volume would be 30 divided by 2. That's 15 milliliter into sigma values again. Pretty simple if you know that some relationship. Again, this is the showing the relation between volume and pressure. So therefore, it is about the Boyle's law. Everyone good? Okay, I would like to try these. Question 4, question 3, 4, 5, 6. Now, please. Try to think about what factors of the gases you have and think about their relationship. And can you guys also write the what laws according to what scientists at the end of your answer, please?
Question 3 have a typo. It says 273 Kelvin pressure.
Should be the temperature. Typo. Thank you. Let's fix that now. Oh. Oh no. Finish?
Yeah, can I get it?
Okay, let's check your answer now. Question 3, a hot air balloon at 273 Kelvin has a volume of 5 liter. The temperature is increased to the 365 Kelvin. If the pressure remains constant, what will be the new volume of the balloon? So what is this relationship here? It's about the temperature and the volume. And what is the relationship? Are they directly proportional? Yep. Indirect means as directly proportional to the between temperature and volume. So in other words, V on T is equals to K. Or either way around, the V on T doesn't really matter in that case. So let's have a look at that here. So, first of all, we have the hot air balloon. So given that 273 Kelvin, that volume is 5 liter. Using the relationship, that'll be 273 on 5 is your constant value. And in fact, that is same as what? The new temperature, volume of the new temperature, which is 365 on the volume, new volume. Therefore, the new volume can be found by how is equals to 365 times 5 on 273. Yep, and by doing so, 365 times 5 divided by 273, you'll get 6.68. So you change that into 2 sig figs, it is 6.7 liter. Make sure you follow the same unit, 2 sig figs like this. Again, and whose law is this? Temperature and volume is Charles. Now question 4. A hot air balloon at 273 Kelvin has a volume of 355 liter. The temperature is increased to 395 Kelvin. If the pressure remains constant, what will be the new volume of the balloon? So let's think about this. 273 Kelvin and 355. So again, as a V on T is a constant value, means that we have 273 on 355 is the constant. And given the new temperature of that, which is 395 of the volume, therefore new volume is 395 times 355 divided by 273. Okay, so that is 395 times 355 divided by 273. You to get 513. So in that 360 value, it should be 514 liter in 3 sig figs. Again, temperature and volume, that's Charles' law. Question 5. The temperature of the air inside the car tire is initially 20 degrees Celsius. The car tire is left in the hot sun, and the pressure inside the tire rises from the 1 bar to 1.15 bar. What is the new temperature in this tire? So what is the factors here? It is about what? The temperature and the pressure. And what is these two relationship? Are they directly or indirectly proportional? Temperature and pressure are directly proportional. Means that T on V and P, or P on T is K. Yep, got that? So as we have 20 degrees initially and the pressure is 1 bar. So using that relationship, T 20 on 1 is a constant value. Okay, as we need to find a new temperature, the temperature is T on the new pressure, which is 1.15. Make sense, everyone? Okay, so new temperature will be 20 times 1.15. That is 23. Unit is degrees Celsius. Make sure you follow the unit you have in your question. That could be a simple trick. Okay, and as we have a relation between temperature and pressure, this is the Gay-Lussac's law. Everyone good? All right, question 6. Now we have a gas in the sealed container at 25 degrees Celsius. Is heated in an oven. If the initial gas pressure was 1 bar and the final gas pressure is 1.6 bar, calculate the new temperature. Again, this is about Gay-Lussac's law. We have to deal with the pressure and the temperature. So given that we have a 1 bar and the 1.6 bar, new temperature, so given 25 degrees Celsius on the 1 bar is a constant value. That is same as what? 1.6 bar over the new temperature. So the T, which is the new temperature, would be 25 times 1.6. So 25 times 1.6 is equals to 40 degrees Celsius in given two sig figs values. Everyone good? Yep, easy. So it is important to know that whether they are directly or indirectly proportional, and it's not really how to imagine. Think about the rush hour train. Okay, think about the rush hour train. That would be probably the best way to think about the pressure, temperature, and volumes relationships. Any questions up to here? Okay. All right. What about this? What if we have some situation where we have to deal with the 3 factors? So we have pressure, volume, and temperature. So let's start from here. according to Boyle's law, it is saying that the PV is equals to K. The relation between because they are directly, they're indirectly proportional. Okay. Next law is the Charles' law. According to him, we know that the V on T is equals to K, which is a constant value. Lastly, according to Gay-Lussac's law, we know that the P and P is directly proportional, means that P on T is also the constant value. Now, what if we combine them all? So if I combine them all, we get some constant value as we're adding all of this. And think about the relation between these two. These three here, then we can have T on our denominator. That is same as what? P and V on the top. Which means that the relation between P and B is directly proportional to the temperature. Or you can say V is directly proportional to the pressure, the temperature, but this will be indirectly proportional to the temperature again. Not the temperature, sorry, the pressure. Oh, other way around. So volume and temperature are directly proportional, and pressure is indirectly proportional like this. So I'm just combining all the relation between three factors. Then we are getting some kind of rules like this. This is known as the combined gas law. So not from one or two or three people, there are combined laws like this. Now, combined laws can be used in various ways. So we have this. So in your example on page 130, let's have a look at this question now. So we have P on B on T is the K value, constant value. Question 1. Student measured the pressure and the volume of carbon dioxide at 25 degrees Celsius to be 148 kilopascal and 15 mil. Now gas was then heated to 200 degrees Celsius. Calculate the new pressure if the volume is increased to 30 mils. So thinking about relation here again, bring up the combined gas law that PVT is the constant value. That is what? We have a pressure of 148 kilopascal. I like to put the units here to get the unit correctly. So, and the volume of 15 mils. On that temperature of the 25 degrees Celsius, which is same as what? Which is same as what? We now have the temperatures being increased to 200 degrees Celsius, and we also have the volume is now we have the 30 mils. Okay, but the question is ask you to find the new pressure. Good. So pressure will be, new pressure will be 148 times 15 divided by 25 times that to 200 on 30. And Sky, what'd you get? 592. Oh, that's huge. Yeah, 200 degrees Celsius. 592, yep, seems to be right. Just double check. (592 units? Kilopascals. To be aware what units you have in there too. So fix that into 3 sig fix. Where we have 3 sig fix here. Yeah, that would be the 3 sig fix value. This is how we use the combined gas law again. Important to remember that this PV on T can be the constant value. So one thing about this, okay, we will learn about something called the ideal gas law next week. But something you need to remember from here is we can get some, as they have some clear relationship, we can get some relative values. It's all going to be a relative in here. Now let's do the question 2. Okay, can you guys try the question 2 now? I'll give you 2 minutes to try yourself.
How many six pigs do we use?
How many siblings do we have?
3.
Yes.
But then the answers
Did you get the 2, 5, 5, 6?
2, 5, 5, 6. Yeah.
Fix that into 3 6 pigs.
Oh, so do we just do it?
Yep.
Oh, we like that.
Oh, it's up to you.
Then we did times 10. Change it.
Oh, sorry. Yep. Forgot the 0.
Oh, okay.
Okay, so just like what we have done in the question 1, as the PV on T is a constant value, we can find the value by the 96 times 500 on 25. That is equivalent to what? P times 338 divided by 450. Alright, so to find the P, make a subject to P, then you to get 2556.21. Make sure you convert that, change that to 3 cyclic value, which is 2560 kilopascals for the given cyclic value here. Everyone good? So this is how we use the combined gas law. So I'm just combining the rule, the law 1, 2, 3 for the combined gas law of the PV equals to PV on T is equals to K. The last law I'm going to introduce today is known as the Avogadro's law. Yes, we know about Avogadro's. Where will you get the Avogadro's from? The number of what? Number of moles. So we say the Avogadro's number. We learned about Avogadro even when we learned about the moles, saying that 1 mole is equals to the 6.0332 times 10 to the power 24 atoms. That number itself is called the Avogadro's number. Not the avocado's number, by the way. There are some people actually really write it using the avocado numbers. The Avogadro's number, right? Please. So, as we can predict from his name, it will be related to the moles. It will be related to the quantity. And the rule is pretty simple. What I mean is, hey, when we increase the number of the moles, the volume will be eventually increased. Isn't that pretty simple? Okay, thinking about when you get a rush hour train again, train's about to be exploded because it increased the volume. Because pressure is actually related to that. But you can think about putting more of the particles, gas molecules means that we increase the volume too. So that's the last Avogadro's. Probably the most simple one, okay? Because from the name, that is about the N, number of mole, and the volume. That is volume is directly proportional to n. Therefore, V on n, V is equals to Kn, like this. Or saying V on n is equals to K on the other hand. Okay? As we learned from the chapter 3, when we learned about concentration, do you remember that there are several ways to find the number of moles? Okay, as n was equals to m over molar mass in the chapter 2.
Yeah.
Well, we also learned that n is equals to CV. Don't worry about this. Okay? We're gonna come back in the holiday. Another rule is, as we know the volume, this is what? About the solid some other state. This is about what? This is about aqueous solution state. So we will learn about V on n equals to K as some sort of relationship for the gas state. So there are certain rules. As you can see from here, volume of gas, mass, and concentration, we are always finding what? Moles. So the way we can find the moles, it can be various. By the way, the way we can find the number of particles is always from the moles times that to the Avogadro's number here. Okay? But the relationship is from the volume of the gas. If we know the volume of the gas, we are able to find the number of the particles, number of the moles. How do we do that? On your page 113, this is something that you need to highlight and you need to memorize. I know, hang on. You don't need to. It will be given on your formula sheets, by the way.
Oh.
It's here, right here. But it's good to know that this value means this. All right. At 100 kilopascal and 0 degrees Celsius, we call that as, that's standard temperature and pressure. Sorry, I was wrong about STP previously. So STP is for that 100 kilopascal and 0 degrees Celsius, which is 273.15 Kelvin. Okay? If we have 1 liter of the any gas molecules at STP, that would be 1 mole, should say 1 mole of any gas molecule as particle at STP. This will take a volume of 22.71 liter. It's unofficial. It is just certain rules. Always. Doesn't matter. Doesn't matter you have a H2, O2, H2O, Cl2, any gas. 22.71?
Isn't that at 0 degrees?
That's at the STP.
On the book it says 0 degrees.
Yeah. That's known as the STP.
Oh, it's 0 degrees.
The STP is at 0 degree. Standard lab condition, SLC, standard lab, so something like we're performing in the room temperature here. That's 25 degrees Celsius or 298.15. The volume, as we learned. Brandon, what was the relation between volume and temperature again? When the temperature is increased?
When the temperature is increased, the
volume is increased. It's directly proportional according to Charles' law. It means that as we see the temperature is being increased from 0 to 25, you will see the actual increase of the volume too. It means that 1 mole of any gas, this is important, any gas molecules at SLC, which is standard lab condition at 25 degrees Celsius and 100 kilopascal, the volume would be 24.79 liter. So you see that volume is being increased as due to the increase of the temperature. But this is a set value, always going to be like this. So you have to be careful. You have to be really careful what conditions you have. You can either have STP, you can either have the SLC. Whether you have that STP or SLC, it will be given on your first page of the formula sheet. So it was saying at 0 degree and at 25 degrees Celsius. You can find that. So I will give you that when you take the topic test or module test later on too. And same in your school. So in other words, we can find the volume of the gas by times to find the number of moles times the Vm, which is the Vm is the given units over here. Okay, let's have a look at some example with this. in class exercise 4.4. So question 1, calculate the volume of the 50 moles of neon gas at 100 kilopascal and 0 degrees Celsius. Sky, what is that condition? Is that a STP or SLC?
STP.
That's STP, so that's a standard temperature and pressure. So we have 50 moles at that. How do we find the volume? So volume of the gas can be found by number of moles times Vm, which is given at this constant value. Okay, just try, and it's got to be really easy. The N, as we have 15 moles, and this is the volume per mole, means that it will be 15 times 22.71. That's 340.65 liter. So if you have this many of the neon gas, that will be the volume, it will occupy the volume of this much, 340.65. Now, change that to the 2 sig fig, so it will be 340 liter in 2 sig figs. Okay, B, Brandon, what conditions do we have? STP, and we need to find the number mole of the nitrogen gas. Do not get afraid of the N type of the gases we have. The rules apply the same. Means that we can find N by the V gas on Vm. V gas is given as what? 78. As we know, it's a STP that divided by 22.71. So 78 divided by 22.71, you would get 3.43. So fix that into 3 sig fig values. That is 3.43 a mole. Question C. The volume of 6.5 gram. Now, we have 6.5 gram, Sky. We have 6.5 gram here. So we're not dealing with what? Moles yet. What should we do? Thank you very much. So this is how we use the N equals to M over molar mass. As N is equals to M over molar mass, what we know is we have 6.5 grams of the oxygen. So N is then 6.5, which is the mass of the oxygen, divided by 16. That's the molar mass of the oxygen. By doing so, divided by 16, you will get 0.40625 mole. I'm going to leave that number here to follow the next calculation. Now, this happened at SLC. So what was the temperature volume at the SLC again? Yep, so the volume Vm at SLC? 79. Yep. Liter, therefore, to find the volume, V gas is equals to N times the Vm. That is 0.40625 times that, 24.79. Then you'd get, in 2 sig fig value, you'd get 10 liter in 2 sig fig. Okay, so do not get afraid of those number of moles. Again, this is very simple. But the trick can be like, you would think like grams is actually that. Now, I would like to try the D by yourself. Think about it. Okay, Brandon, this is something that probably you started learning in school. When you're given the total number of the molecules, you can convert that into unit of moles by dividing into Avogadro's number. Because 1 mole is that. Means that molecules had divided by Avogadro's number, you'd get 1.54 times 10 to the power 4 moles. Okay? And then from the given mole and given condition, the SLC, you can find the volume of the gas is also equals to N times volume of the M. So 1.54 times 10 to the power 4 times the Vm, that is 24.79. Ooh. Then you'll get 3.81 times 10 to the power of 5 liter. Oh, sorry, you have to find in the 4 sig fig, so 3.817 in 4 sig figs. So can you guys imagine that, like how we actually use that different formulas here? Yeah. You can possibly think about how they relate to concentration. That we have a certain amount of the water. Let's say, hey, I have some concentration of the hydrochloric acid that has certain concentration. If we evaporate them all so making into room temperature, whatever, then what if the volume of that? So question can use the different formulas in module end of module 2. And that's possibly can be in your school exam next term. All right, can you try to do this questions, that question 2 on your page 135? This will be the last question that we will do today. Sky, for the chapter exercise, yeah, you can do the one in your booklets.
I don't have question 2.
You don't have this?
Yeah.
Oh, you don't? Okay. So I didn't print it. No worries. Here you go. Finished? Not too sure. You alright, Brendan?
I'm not really sure how to do it.
It's okay.
Do you have to find the molar mass?
You do. So,
Yeah, I don't have a period.
oh, you don't. Okay. Here you go. Oh, this is interesting. Highlight this. It could be the hardest question you can get to.
I also don't have to.
Yep. Don't you?
I'll just use it after.
Okay. All right. Let's start from here. The termite reaction used to industrial weld train tracks together involves the reactions of the iron 3 oxide and solid aluminium to form gaseous aluminium oxide and the liquid iron. What volume gaseous aluminium oxide would be formed at SLC if 521 grams of both reactants was used? Were used. Okay, let's think about this. This is it's not an easy question, to be honest. So look at this closely. When you get questions like this, I always recommend you to start with the balanced chemical equations first. So what we have here is iron 3 oxide. So that's Fe 3 oxide means FeO3. And given that as a solid, plus the aluminium, Al solid. They both react in the high temperature to becomes what? Aluminium oxide, Al2O3, which is gases in that case, and liquid iron like this. So these are what? First of all, check. Okay, Brendan, have a look at this first. Check whether you balance your equation or not. We have this. It's not really balanced. So how to make a balance?
Check the aluminium number.
Yep, aluminium number here. So 2 aluminium and
Check the iron number.
iron number is
And then
2 iron. Very good. We need to think about the coefficient here. And the question is saying both of the reactants are given the mass of 521 gram. So mass of the iron 2 oxide was given at 521 gram. Shall we find the number mole of this?
Yeah.
How to do this? The 521 as N equals to M over molar mass. That's 521 divided by, anyone have the periodic table? Yep, what's the molar mass of the iron? I don't have that with me now. Where are all my periodic tables gone?
You have to find the iron oxide.
For
This is what volume gaseous aluminium oxide will be formed.
yes, true, but we need to know how many moles of the grams or moles of those aluminium oxide will be produced. Okay. Does anyone have periodic table? Okay. What is the mole? Can somebody give the mass of the iron, please? Fe. What's the Fe value? Brendan, you have my periodic table.
159.7.
0.7 plus the how many oxygen? 3 times 16.
Wait.
This.
Oh, I already passed it.
Yep. This is. But you need to show the way you find the.
So 159.7.
Yeah. Hang on a sec.
I gave a wrong iron.
Did ya?
Because I already.
Oh, okay. You mean that's total? Okay.
Yeah.
When you're writing the molecular mass, you must show that the way how you find the value. So not that. Iron is given as 55.85. So 2 times 55.85 plus the oxygen is 16. So 3 times 16. Then what you get is you get 2 times 55.85. I think that was the value you talked. Yeah, you gave me. So 521 divided by that, you're going to get 3.26 mole for the iron oxide in that given 521 gram. Everyone happy?
Yeah.
Now, mass of the aluminium is also given as what? 521 gram.
Yeah.
So number mole of the aluminium, it can be found by N over molar mass, M over molar mass. So 521 divided by molar mass aluminium, that's 26.898. That's 521 divided by 26.98. Then you'd get 19.31 mole. Everyone good up to there? So even though you're given the same number, same grams, the number of moles in that is kind of different due to the molar mass number. Now, why do we need to find the moles? Because I need to think about the molar ratio. Brendan, what was the reaction ratio between iron oxide and aluminium? According to the balance equation here. 1 to 2. So it means that per 1 mole of the iron oxide, we need to have 2 aluminium. But in fact, what we have is we have 3.26 mole of this iron oxide, and we have 19.31 mole of the aluminium here. So do you think we have a perfect 1 to 2 ratio here? No. Means that I can think of here, hey, I can use all of this. We can use all of this. But there will be some excess of the aluminium left. Does it make sense up to here? So it means that, hey, the iron oxide, this is how we say, iron oxide is the limiting reagent, which means that it will limit the whole reaction to go consume all of the aluminium. In the terms of limiting reagent means that this will be, therefore all iron oxide will be used to form the aluminium oxide. Now, if we use all of those iron oxide, which is 3.26 mole,
Yeah.
how many moles of the aluminium oxide can be produced? The mole ratio is, the reaction ratio is 1 to 2 to 1 to 2.
Yeah.
I don't care about this one because we are dealing with what? This one only. So if we make 1 mole of that, if we consume 1 mole of that, there'll be 1 mole of this. Means that, hey, we have 3.26 mole of the iron oxide. So can we say the N Fe2O3 will be same as the N aluminium oxide as the, make sure you write this, and as the reaction ratio is 1 to 1. Everyone happy with that? Okay. Therefore, we can now say N aluminium oxide is what? Is same 3.26 mole over here. Everyone good? And the question's asking you to find what? What is the volume of that in SLC? And how do you find that? The volume of the aluminium oxide can be found by N times the Vm. That is 3.26 times the,
24.7.
thank you very much, 24.79. Then what do you get? Yep, 80.81. So I fix that into sig fig value of 3 sig fig values. Yes. Oh. Unit? Liters in 3 sig fig value. This is how you do the questions in Module 2. Complicated? A little bit? Yeah, I know. So I know you haven't learned about these yet, okay? But now we can think about why you need to focus on the balancing equation. Okay? This is a combination of everything we learned in Module 2, Sky.
Yeah.
So if I make a question, I will make questions like this. If I make a question, I'll make a questions like this.
Yeah.
This is something you will get in your school exam yearlies, but not bad.
Yeah.
So start with step by step. Start with the balanced chemical equation. Always start with that. Okay. This is actually part of your marking, part of the marking criteria. We actually see that, including the state.
How many marks would it usually be?
This one, 3 marks,
Okay.
because this will be 1. Finding about that is 1, up to the so 1 and 1, and then finding that last part with the correct answer will be 1. So up to 3 to 4. Okay, but that's not really. I mean, it looks complicated. The hardest part would be this one, to find what is the limiting reagent, understanding about the moles here. So this is my recommendation. When you get something like in the volume, something in the gram, something in the concentration, find the mole. Find the mole for the reaction. It will eventually tell you which is the which is the limiting reagent. Therefore, you can find the answer for the questions asking there. Make sense? Okay. So your homework is finish up the rest of the chapter 4 exercise till next week. And we're gonna finish up the chapter module 2 by doing the chapter 5. That's ideal gas law.
So all of chapter.
All of chapter 4.
Yep.
Okay, answer. Brandon, the answer for the chapter